Greeting Earthlings, if you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. In the previous episode, we finally were able to transmit a command from our original NASA Up Data Link Test System, or UDL for short, over to the spacecraft and decoded it all the way through the complicated chain of original electronic boxes that were in the spacecraft. The transponder, the premodulation processor, the central timing equipment, and the Up Data Link decoder. And that felt like a major achievement. However, the result was admittedly somewhat underwhelming. We made a multimeter beep on the space side of the link. Alright, that's first command 4601, that's abort relay 1. Send. Oh, works. Alright, we got it. So that was it.
Right there.
Oh hum. So in this episode, we'll give the Up Data Link the grand workout and demonstration it deserves, sending commands to flip relays and lights, take control of the central timing equipment, and exercise the most powerful capability of them all, controlling the Apollo guidance computer remotely via its disk key. In essence, we'll show you how you could have hacked the spacecraft if you had been so inclined and well equipped in 1969. I'm sure NASA will be glad that we only figured this out 50 years too late. So we were looking at something fun that we could connect our relays to, and a panel of lights would be a good thing. So the idea is to light up one of the lights that were controlled by the UDL in the actual missions. There are two that I am aware of, the abort request light and the crew alert light. The crew alert light was on the main caution and warning panel. In this diagram, you can verify that it is directly wired into the relay K2 of the UDL. Interestingly enough, the crew alert light was only controllable by the ground. It could also only be reset by the ground and not by the astronauts. The other light controlled by the ground via the UDL is the abort light. It was on sub-panel 1B right in front of the commander, where the emergency manual control for boost, entry and abort are also located. Looking at its wiring in the schematics, you can see that the light is wired both to the abort A relay and the abort B relay in the UDL. The only difference is that the abort B relay is resettable by the crew, while the abort A relay is resettable only by the ground. You can actually double check that in the UDL schematics. Here is the abort A SK1 relay, and it can be reset from the ground via this wire. But it has no reset connection to the front panel. The abort B relay does have such a connection, called reset override, leading to the up telemetry command reset button, and is pointed out in this side note that says crew cannot reset K1 to K5 relays. Which are these relays over here? The side legend tells us what they do. We already know that the abort A and the crew alert lights cannot be reset by the crew. The ACE refers to the automated checkout equipment. The ACE was used to talk to the Apollo guidance computer while on the ground. As we'll see later, there was a separate wire path for transmitting ones and zeros, so apparently you can block either of these. TRDC stands for Tape Recorder Data Conditioner. This one is even more arcane. The TRDC was an electronic box in charge of retiming the data bits as they were replayed by the onboard tape data recorder to straighten them out before transmission. Today it would be called a clock and data recovery circuit. Apparently the ground could bypass that box and send the raw, unretimed bits if the TRDC were to malfunction. There you go, you know everything. Alright, we rat hole again, back to our abort light. The spacecraft operations manual tells me that the abort light was used by the ground to request a manual abort, but only as a backup to voice communications. The commander would then have to initiate the abort by rotating his translation controller handle. This is indeed confirmed by the wiring, which does nothing else than turn on the light. The actual abort signal was generated manually by the handle rotation. There were of course automatic and triple redundant abort circuits that needed no astronaut intervention, but for relatively few conditions. They are detailed here: too much pitch or yaw rates, too much roll rates, or not enough thrust. That's it for the auto abort. For all the rest, the ground would turn on the light via the UDL, as we are about to reenact here, and the astronauts would have to react to it. We'd love to have a real Apollo caution and warning panel to light up, but we have the next best thing, a period-correct warped panel of roto tail lights from Marcel's collection, of course. These indicators were used all over the place in Apollo control rooms. The panel arrived way more banged up than the auction pictures suggested, so while Mike and Eric are busy wiring up the UDL, I need to do a little unbending. So this one was just bent so much I had to take the rods, and the rods were bent at 30 degrees in there. This is the last one, it's pretty good. And this one. All right. Look how mangled that thing is. Just do it by eye. Oop. Right. Ta-da! Okay, so this is why these are called roto tail lights. You rotate them, and then you can change the bulbs from the back, which is now the front, so no need to dismantle the thing. So everyone has left, and I still haven't finished my panel, so at least it's back together. There are some cables that are mangled deep inside here. Fortunately, I have the extraction tool, which sometimes works. There we go. Oh yeah, I see the problem. It is attached, but it's been partially cut. Okay, so that explains that it's probably part of the big accident that bent the whole thing. Alright, so let's see. So this should be 1, and then 2, 3, and it kind of makes sense. We can hook it up to the data link and see if we can light some. Hey guys, you've wired up a few more things?
We have. Yeah, we've got a big light panel that used to be round and is now flat.
Oh, this one, yes. We're going to turn relays.
Yep, so we'll flip the relays.
Lights through the relays.
Turn on the lights.
Yeah, turn on
We've
the
only
lights.
got 2 of them connected, but
For
we
now,
should still be able to see.
I've been trying to motivate Mike
It's a lot of wiring.
and Eric to wire the 72 lights, but I've had no success. The connectors are so impossible. They are so dense. Anyhow, it's a lot of work for a little reward. And I've been busy making tapes that could potentially turn those on, so I'm going to try that. So now the question is, what is the correct binary command to turn our lights on and off? We now have two lights, one connected to the abort A and one connected to the abort B relay. I sort of messed up. I wanted abort A and crew alert, but I did not give Mike and Eric the correct relays. Anyhow, that will allow us to demonstrate the difference between abort A and B. The relays in the UDL are of the fancy latching kind. You can spy them at the bottom of the UDL. It's the kind that remembers its state, so there are two coils per relay, a set coil and a reset coil. The coils are actuated by the logic block below them. Fortunately, there is a table on the side that summarizes how it's encoded. The first 3 bits are the vehicle address. You could wire up your UDL to respond to one of 8 different vehicle addresses. The command module was assigned to address 4, and that's how we configured our UDL in the previous episodes. The next 3 bits are the system address. The system that flips the relays is called the RTC system and uses system addresses 5 and 6. RTC, by the way, stands for real-time command, and when you overhear the Houston controllers referring to sending RTC commands, it means they are sending commands to flip relays via the UDL. Other systems addresses were used for test commands, controlling the AGC, and setting the central timing equipment. We'll exercise them later on. So back to RTC commands. On system address 6, bits 7 to 12 indicate which relay coil will be activated. These 6 bits form a 2-digit octal number, which happens to be the number drawn on the relay coils. In our case, we need to tickle coil 00, 01, 06, and 07. You can see that there are no coil numbers with a digit 8 or 9. This is indeed an octal numbering system. There are an additional 4 codes for the system at address 5 called the salvo reset codes. These reset a whole bunch of relays at once. Here is the list of all the relay coil numbers next to their function. Essentially, this is a real-time command cheat sheet, an Apollo hacker's dream. It also sheds more light on what the salvo reset commands do. The first salvo code gets you back to a normal flight condition, no alarms, TRDC in normal mode, ranging off, reset the PCM telemetry settings. And the second one resets the communication system. For our first demo, our commands are therefore going to be: turn on abort A is 4601, as in vehicle 4, system 6, coil 01. Turn off abort A is 4600, which is the same for coil 00. Turn on abort B is 4607, and turn off abort B is 4606. But we are not quite done yet. We need to punch a command tape for our clunky UDL transmitter. And it is not as simple as punching the command numbers in. Oh no! The UDL tape reader does not use the ASCII encoding that everyone else used to punch their 8-bit tapes. Instead, it uses another code that MasterCan cracked many episodes ago and has some embedded error checking features. Here is the reverse engineered list from my notebook. For a 0, you have to type in an 8, a 1 is actually a 1 by pure accident, a 2 is a star, and so on and so forth. Many are special control characters. To add insult to injury, they also hijacked character bit 7 and parity bit 8 as special tape control bits. Plus, you need to add a 3-digit command number preamble, which will be read and indicated to the left of the current command, but not transmitted. And then you need a leader and sync command to start. So making tapes quickly gets complicated. I ended up with an incomprehensible file of mostly special characters, which I then sent via serial to my ASR33 teletype, which we repaired some years ago. I knew it would come in handy one day. And finally, out comes a punched command tape, which I eventually got right. Okay, done. Hopefully this is a good one. We made a few bad ones. We'll try to see if that works. Okay. Okay, 000 got the start. Alright, that's first command 4601, that's abort relay 1. 4600 clears it. Relay 1 again. Clears it. 4607, that's abort relay 2. 4606, that's clearing that relay. Try again. Yeah, we got it. Let's try that. Can you put the receive on up? Okay, I'm sending stuff, that's good.
We're seeing it on the scope.
Okay, so turn it back to normal. Now I should have turned it. Oh no, not yet. I haven't turned the relay on yet. If I do this, I will. No. No cigar.
Are we looking at the data validly?
Okay, well, let's keep it on. No. Neither. That should be the second relay. Am I selecting the right thing at least? Did you hear relay click at all?
No.
Do I have the right polarity? Yeah, we did. Should I try, you know, I could try my older tape where it worked, right? Let me try another tape. Okay, 0. Anything? Oh, sorry.
I heard a click.
Did it click?
I heard a click.
Okay. Then you should hear another click here. You hear another click?
Yep. Yeah, it's definitely
It's clicking.
changing. I'm seeing it.
It's clicking, but our lights are not indicating. Oh, did I give you the wrong pin out?
Yeah, maybe that's not.
Yep, that's what I did. I gave Eric the wrong panel pins. So let's try this again with feeling and the correct panel wiring. So that should be abort 1. I'm going to tape stop it and give you the command. See if it clicks. It did!
Yeah.
Alright. Then I keep going. And that's going to be clear abort 1. Sending it. Alright, we have command of our spacecraft. And then that should turn the other one on. That's abort 2.
That's abort 1.
Oh, I have to twice abort 1?
Yeah.
Yeah, I do have twice abort 1.
Hey, there's abort 2.
Okay. Okay!
Can you turn on abort 2 again?
You want to do what?
The command reset switch.
Oh,
we
only
can turn
works
off
on
the
abort
abort 2,
2.
but not abort 1. That's
Okay.
correct.
abort 2.
Yep.
Tell me you can reset that one?
From the switch here, command
Okay.
reset.
It works?
It reset the relay.
Yeah, and abort 1 you cannot reset it for
Right.
some reason. And if we had the patience we could wire more lights, but instead, since we don't have the patience, but we wired the CTE, where's CTE? Over there. And that's this guy over here. It's the one that gives us time in the mission. And supposedly we're supposed to remote control it. So I've made a tape for that.
Yep.
We'll see if that works. Before we leave the subject of RTC commands, let's briefly scan the ones we have not already talked about. You'll quickly discover that they all have to do with controlling the data communication system. turning the transmitter power amplifier on, resetting the antenna configuration, turning ranging and telemetry on, switching the telemetry bitrate, and controlling the tape data recorder. These were implemented as shadow switches to the astronauts' manual switches on the control panel. The ground control relays always have precedence over the command panel switch positions, unless you flip up the magic command reset button that we just demonstrated, which would give back control to the panel by virtue of resetting the relays. In practice, the astronauts were rarely bothered with setting ranging, telemetry, and data bit rates manually, nor did they have to manage the tape recorder voice and data dumps. This was done from the ground via RTCs, lightening the workload. However, if you had to, you could flip the up telemetry switch, the same that we just flipped up to reset the relays, to the down off position instead. That would shut out the ground commands entirely, in case you were worried that the Soviet equivalent of CuriousMarc and team was tinkering with your spacecraft. Last but not least, you probably noticed that there are no RTC commands to actually fly the spacecraft. This was done instead via the Apollo guidance computer commands, which we'll demonstrate later. But before that, let's play with the central timing equipment. The CTE produced reference frequencies, timing pulses, and second ticks used throughout the spacecraft. It also provided the mission clock, both in parallel and serial form, which was used to timestamp every telemetry message sent back to Earth and to sequence automatic events in the SIM bay, the service module bay with all the external scientific equipment. It is one of the rare Apollo pieces of electronics, besides the AGC, that use integrated circuits. We got it working back in episode 25 and hooked it up to an HP Nixie instrument display for extra vintage style points. The ground could control this clock remotely via the UDL System 4. It's pretty straightforward. You use vehicle address 4, system address 4, and then send a series of 6-bit binary numbers for the seconds, minutes, hours, and days. Once received, they are sent out as that many pulses to set the appropriate counters on the CTE, as if you were setting a digital clock by repeatedly pressing on the minutes or hours button. But there is something very odd about the bit structure of this command. Maybe you even spotted it already, but I sure didn't at first, which is going to lead to interesting results. So here we go, that's my CTE messages tape. And what did I do? This was complicated. One is going to reset, supposed to reset. Then I go to 4 days, 3 hours, 2 minutes, 1 second. Then I go to the landing time of Apollo 11, and then I go back through the sequence a couple times. It took me a whole orbit to figure that one out. So watch this. 0, 0. Okay, so that should be now 440000. Let's see if I. Yeah! It worked. Okay, let's try the next one. So this one should be 01, 02, 03, 04, if I get the right order of stuff. 01, 06, 02. So I got my encoding wrong in the second bit. Okay. I'm getting there. I need another orbit. This one should be the time of landing. Oh no, I got it completely wrong. It's 4 days, 6 hours, 55 minutes and 40 seconds, and I got 55 instead of 45. Do I get 6? I got 3 instead of 6.
Is this just an Endianist thing?
I think so. And it looks that they switch from big endian to small endian as they move from vehicle address, system address, and then this obviously means 4, so that's the most significant bit over here. But here, the seconds has the most significant bit at the other end. So there's some reversal here that I have to figure out. So I think I sort of figured it out. I put my time in seconds, minutes, hour, days, which gives me that binary representation. Now I have to reverse the endianness. So 0,000,001 becomes 1,0,0,0,0,0. And then I do that for every number. And then I have to split them in 2 octal numbers. That gives me 4, 0, 2, 0, 6, 0, 1, 0. And then this I have to encode with my little tape cheat sheet. And then I'll have to add 4, 4, but with the opposite endianness. So I think I have it. So the time of landing is FS 8 NAC Bell pound 818. That's the landing of Apollo 11. Try again. Alright, CTE endianness change. Okay, so that should reset the time. It does. Next one. So that should be 4, 3, 2, 1. Oh yes, I got it. That was the bit order. And then somebody remembers the time of Apollo 11 landing. Day 4 hours 6 minutes 55 40 seconds. Day 4 hours 6 minutes 55 40 seconds. We've landed.
Nice.
Yeah. All right. Oh well, it worked, but I slightly messed up again. The get time of the Apollo 11 landing per the contact light is 6 days, 6 hours, 45 minutes and 40 seconds, not 55 minutes and 40 seconds. But you get the idea, and I don't feel like making another tape.
Engine arm off. Port 13 is in. We've had shutdown. We copy you down, Eagle.
But what a thing, they changed endianness in the middle of the message. Okay, well that's pretty cool. I can reset time in space. Okay, so are you guys busy trying to wire the AGC?
That's correct.
So because the next thing we want to do is wire the AGC.
Yep.
Because this whole system could basically control the entire AGC.
Yeah, it gives you the ability to press DISCI keys. So anything you can do through the DISCI, you can do from the ground.
Yeah, and then on the way down, it could read anything, of course.
Mm-hmm.
It's a sort of remote desktop for
Yeah, yeah.
So we saved the best for last. You could control the Apollo guidance computer from the ground just like the astronauts did, by simply sending DISCI key press codes. Since the AGC continuously transmitted what was displayed on its DISCI screen via down telemetry, Houston could operate the computer remotely if they wanted to. For that, you used System Address 3. The data payload consisted of a 1-bit, a 5-bit key code, its 5-bit complement, and a 5-bit key code repeated again, with an endianness that is not quite specified, but we'll figure it out. The resulting 16-bit data word was transmitted serially to the AGC by pulses over 2 wires, one to input a 0 and another one to input a 1. The AGC was then responsible to check for validity. Note that 2 switches, one on the command panel and one in the lower bay, had to be set both to the accept position in order to grant remote access to the AGC. Generally, that was not the case, and the ground had to specifically request computer access before they uploaded anything, and access was turned off right afterwards.
It's 16 bits you need to send for every key.
Right.
Every key is going to be its own UDL message.
Okay,
It'll be a leading 1,
okay,
and then the 5-bit key code,
okay,
and then the 5-bit key code inverted,
Right.
and then the 5-bit key code uninverted again.
Yes, and then we have to split it. Well, with the right endianness.
Right.
It's good that we did the clock before we do the AGC.
I think the clock is reversed from the AGC.
Good. Sadly, we don't have the real AGC with us anymore, but Mike still has his gate-exact FPGA replica. He breadboarded 2 input stages for the 0s and the 1s lines, and we should be in business. You brought your replica?
Yep, so I've got both the AGC and the monitor programmed into that FPGA.
Oh, it has shrunk? That's a new one.
Yeah.
Alright. It's a long time we didn't have an AGC running.
Yeah.
At least here. I'm sure you had it running at your place.
Well, it's been a while since I've had the blinking lights going at my place, too. Yeah, so what I'm going to do is I'm going to set up my wildcard register to monitor address 45, which is what the update is going to get shifted into, so we can see what bits the AGC is getting.
Okay, so we can try first a simple tape where we just select the AGC as a subsystem, set it 0s, for example.
Yeah, we could do that. It'd probably be easier to
Just give it real data.
Well,
give it one key code.
Yeah, if we put up like verb 01, noun 01, whatever. When you like transmit a verb key,
Right.
we would see
Verb.
the verb disappear.
Let me see if I get the hang on how to make the tapes quickly.
Moments later.
So we're going to go for the AGC control, the disk key. And that's my first stab at programming it, so it might be full of errors. Zero. Okay. Okay, you're ready. This is reset.
Okay.
You see anything?
No, but that's
You don't expect to see anything. Verb.
nope. No.
Do you see the data coming through?
Nope.
Did I miss something? System. Oh wait. There's something wrong with my. It didn't sync up correctly.
Oh, okay. Oh, it would help if we turned the UDL on.
Okay, try again. But I was having the wrong command here. 0, 0, 1. Okay, so that should be reset, I think.
Okay.
Okay. And this will be verb.
Okay. Yes.
Okay. And this will be 3. And this will be 5. It's working?
It's working.
This will be enter.
Yeah, it's doing the light test.
Oh! Wow!
Nice.
Excellent. I'll do. So do I need to wait, or I can do?
It's done.
Okay. So then I do. I think I have a reset. Then I have verb.
That did not take.
Oh yeah, I have an error. I am wrong over
Yeah,
here.
you got something there. Really
So I am missing a bit somewhere. Let me try to replay the tape. 6, 7. Okay, I have a problem at 7. Okay, let me fix that.
Soon after.
Okay. So we start again. I think I found a mistake in my program. So here we go. Okay, you are here on your side?
Yep.
Okay, so reset V 3 5 enter.
Yep, you're doing the light test.
Excellent. Do I need to wait for it?
It's done.
Reset. Now I'm good. V 3 7 enter. 0 0 enter.
Perfect.
And then reset.
Yep, you're in two.
Whoa! That's pretty good.
Yeah.
I think I can run it all in one fell swoop. See what happens. I'm just going to blast it. Okay guys, witness that awesome achievement of computing. Okay.
Yeah, it's fine. I don't know what was up with that.
3, 7, enter, 0, 0, 2.
Looked like a lamp test. Not bad.
Yeah.
We just need a real AGC to do this and a real diski.
That's advanced computing, but we can do anything we want with the diski, basically. And indeed, NASA used the diski uplink capability extensively during the real missions. Here is a list of all the uploads from the Apollo 15 flight. Granted, there are a few for the instrument unit, but most are for the command module or the LEM computer. They included navigation updates, burn lows, time sinks, and landing site updates. And if you are as curious as I am, you're probably left wondering, how did they do this in a real mission? Did they actually type into the diski from their consoles? You sure wouldn't want to punch a paper tape to send a message to the spacecraft. Or would you? And how did they get these commands from Houston to the remote tracking sites and then to the spacecraft itself? Doing this with 1960s technology was a fascinating tour de force and merits a video of itself. Hopefully coming up in a future episode. See you then!